A key concept when working with Bezier splines in 3ds Max is that of interpolation. When we created splines earlier on, we created vertices and those were then connected together by segments. Those segments could be either linear or curved. When they were linear, all that was needed to fully describe the line is already there. We have the endpoints and these describe a line through 3D space. However, when that segment is a curve, the mathematical curve between the 2 points needs some way of defining some kind of approximation of the curve using only straight lines. Why do we need straight lines? Well, as I stated in DVD1 in this series, all 3D surfaces, even those based on curves, have to be converted to polygons to be rendered. This means that we have to segment the mathematical curve so that it can be easily formed into a polygonal mesh. This is realized in 3ds Max by placing secondary vertices, or as they're known, steps, between each of the segment's end vertices. Then a straight line is drawn between each step and the end vertices. When we have one step, we get one extra vert placed halfway between the two endpoints of the segment. Let me just show you this in the viewport here. I actually have a spline that you can see here, and it has two segments, one which is linear and one which is curved. And you can see we've got a very, very nice looking curve here. But that's because it has a large amount of interpolation. In other words, it has a large number of steps along this curve here. So if I just unhide a copy that I have of this curve here, I'm just going to show this here. This is exactly the same line, but we actually have it set up at the moment so that we have no interpolation. In other words, we have no steps. But it's exactly the same curve, it's just that no interpolation is taking place. So when I increase the steps to 1, you can see that it places a step here, which is a kind of virtual vertex. And instead of drawing a line between the two endpoints of the segment, it now draws it between one endpoint and the first step and the first step and the next endpoint. If I put steps up to 2, you can see it's pretty predictable what it does. It adds another step, and you can see each one is 1/3 along the spline. So it basically subdivides the spline by the number of steps, so you get 3 subdivisions, as you can see here. If I put it up to 3, then we get 4 subdivisions, so we have 3 virtual vertices, these steps, and in between each one is a new line. Now, if we crank this up here to 10, you can see that we get a pretty good approximation of the curve when we get up to, say, maybe 10 steps. Now, in other circumstances, many more steps might be needed, and in other cases, less steps may be needed. But of course, when we have this kind of thing going on, as we saw with polygons, there's a kind of law of diminishing returns going on. And what I mean by that is that as we increase the number of steps, and therefore the number of segments, we get closer and closer to the mathematically perfect curve. And at some point, by adding more steps and more segments, we're not really going to see any real difference in the quality of the curve. Once we get up to about, as I said, say maybe 10 segments, then we get a pretty good curve. And once we go above that, we're going to see a law of diminishing returns. But the amount of steps that is actually needed is always based on how curved the line is. If it has a very low level of curvature, then a low number of steps is needed to approximate the curve. If it's very, very curvy, very, very sharp curves, then you need quite a large number of steps. Whenever we're working with splines and interpolation, we'll always be seeking out a sweet spot. And by that I mean a level of interpolation, a number of steps, which gives us a nice looking curve, but which doesn't add any more polygons to the resulting surfaces than is actually needed. If you have a very large number of steps, that will mean you have a very large number of segments, and the resulting surface will have a lot of polygons in it. And that isn't to be desired. Obviously, more polygons means that the model is going to take up more disk space and also is going to take longer to render. So as you can see, interpolation is a good thing. It takes a pure mathematical curve and it turns it into a segmented curve line that we can then tessellate into a polymesh for rendering, and also it allows us to work on those polys if further modeling is needed. There are actually some issues. What happens on a segment which is linear in our editable spline? Well, the truth is it also can end up being interpolated, with just as many steps being used on the straight line as is used on the curve. And from these steps, extra polygons are created. As you can imagine, this is something of a waste considering it's basically a straight line. And a straight line can be easily represented with polygons with just one polygon. So really, it should be not actually interpolated. So let me just show you what I mean by that. If I click on this spline here and I go to rendering, we have some options here for actually very quickly displaying this spline as a mesh. And this is actually a very, very quick way of producing what I would describe as being a loft, something that we look at later. Effectively, you're taking a circle and you're kind of lofting it along this curve here. It's a very, very basic approximation of that loft tool because you have very little control. You can choose the thickness here, how many sides that cylinder has, and also the angle of the vertices around that cylinder. So you can basically rotate the vertices around the path here. So as an example, we can display the render mesh. That actually shows us the mesh that we have. And as I said, you can change the thickness by changing these values here. If I show you this in perspective, you might actually see that it's actually a 3D object here. And we can change the number of sides to make it more cylindrical, as you can see. And you can also, as I said, you can change the angle. And that as I said, rotates the vertices around central core. But if I just go back to top view again, change the thickness back to what it was before, I'll put the sides down to just 3 because it makes it easier to see the segmentation here. You can actually see the problem on here. If I increase the steps here to something higher, let's say 26, you can see that you've got a very, very nice approximation of this curve here, but it's using exactly the same number of steps along this straight line here. And that's a lot, that's a big, big waste really of polygons. It's very inefficient. So the solution in 3ds Max is that we have two options for how we actually define the basic level of interpolation. And we'll have a quick look at these options now. The first of those is the one that we've been using already, and it's called steps. As you can see here, you have this value here, which controls the number of steps along the segment. I would describe this method as being explicit, and what I mean by that is that if we choose one step, we get one step along each segment. And as you can see here, if I just choose this, we get one step here and one step here. If we set it to 2, we get 2 steps. 3, we get 3 steps, so on and so forth. So as you can see, it's totally predictable, and it can be a really great choice when you want a mesh where every segment of the resulting surface has the same number of polygons in it, the same number of segments. In some cases, this can be desirable to make the mesh, as an example, tile nicely all over so that you can then deform it using other tools. If you have some kind of optimization going on along a line here, and this is represented by one polygon, if you then try to bend it, it wouldn't actually have the vertices in it to allow that bend to take place. So in some cases, actually having more steps along a segment than is necessary at the beginning can actually be desirable later along in your modeling pipeline because it then supports some kind of deformation. The second option is activated by clicking on this tick box here, and it's called adaptive. And what this option does is it allows 3ds Max to make an educated guess as to how many segments are needed for a particular segment. This system used a curvature threshold to define how many times a segment has steps to it. The more curvature, the more steps that are added. This means that on a linear segment, you will actually have no steps added whatsoever, whilst on a tight curve, you'll see many steps are added to ensure that the curve is adequately represented in polygons. This method is actually pretty cool, but it does have some pros and cons to it. The pros are that it's easy to set up. You can just choose it as an option and leave 3ds Max to make the decisions as to how many steps to put in any one segment. Another pro is that it's efficient. It only uses enough steps as is needed, no more or no less. And a third positive point is that it's dynamic, which means that if you redefine the curve in any way, the steps, the number of steps will actually change to reflect this. As you make a segment more linear, its steps will drop and vice versa. So let me just show you this. If I click on here and I just open up this dialog here, you can see I can go in here and I can grab this handle, and if I move this, you can see that as I move it, can you see the number of steps dropping along this segment here? This area of the segment, I should say. It's becoming more linear, and therefore the number of steps is dropping. And as it goes towards a line, you can see that the number of steps drops dramatically. Here, you can see that if I make this a little bit more curvy, you can see that as it becomes more curvy, more steps are added along here. And the end result is that you pretty much always get a nice smooth curve. And you can see more steps are added where needed, and they're reduced where they're not needed. So let's just undo that a few times and put it back to the way it was previously. There we go. So as I said, there are also downsides. And one of the downsides is that you have a lack of control here to some degree. If the maximum level of steps around a tight curve is not good enough for you, you'll be forced to use the explicit steps definition system instead. Another issue is that it's dynamic. You know, I said in the last few minutes that it being dynamic is a positive thing, but it also can be a really bad thing in certain circumstances, especially when you're working on a kind of modeling pipeline. This can be a real issue, as when you have some kind of modifier above the spline in the stack, if you're taking the polygons and if you're modifying them, then when you change the curvature of the spline, you may find that the polygon count will change and the vertex count will change, and that means that when the modifier above the spline in the stack takes on the mesh, the vertices that it used to work on will now be in a different place in the mesh, and this can cause a mess basically. So let me just briefly show you that. Let's say we keep it the way it is at the moment, and let's just go in here and put an edit poly modifier on top. We'll go in here, we'll grab some vertices and just move these up here. And let me just grab some of these here, move these out here, and let's just move these down here. Now this isn't really meant to be, you know, a realistic sort of model or anything. I'm just showing some basic editing going on here on the mesh, which is based on the curve. So that looks pretty cool. Now if I go down here and I show the end result, you can see that we can dynamically see what's happening here. If I go into this curve and I start changing these values, you can see that as I change the segmentation, these vertices, the numbers of these vertices is changing, and therefore you're getting some strange looking results here. So let me just do that a bit more. You can see that they're kind of shifting around the mesh, and you're getting some really strange deformation there. Now, in this particular case, it's actually quite predictable what's happening. It seems to be that, as an example, if this vertex here is number 5, and then we change this curvature, it just adds another segment and it bumps it up, let's say, by 4 vertices. But in a 3-dimensional mesh, that may not actually be the case. It may be that this goes out of order in a more dramatic manner, and you'll find that this mesh then becomes a real kind of mess. And that can be a real issue in certain circumstances. So, as you can see, having your mesh be dynamic isn't such a good thing in certain circumstances. If you want to learn more about this topic, then please check out our DVD on proceduralism. This is a title that I produced, and it basically looks into this issue, because what we've been looking at here is actually a procedural model. In other words, we create a spline. From that spline, we create a mesh, and then we edit that mesh. And then we can actually go back down in the stack and we can edit the spline, and that actually changes the model. Now in this case, it actually can cause some unpredictable results. And as I said, that's something which is explored in depth in that DVD. So if you want to look into this subject in more detail, please watch that title. So you may have noticed there's another tick box here called Optimize. And let's have a look at what this option allows now. This option only becomes possible when steps is chosen as the interpolation method. If I just turn off adaptive here, and we'll just get rid of this modifier here, you can see it's a mess now because we've changed the tessellation of the spline quite dramatically. So we'll just get rid of this modifier. And this option is only available when steps is the chosen mode, because optimization is basically implicit in the adaptive method. It is in effect one big optimization. You know, if it finds a line, it'll use very few steps along that line. If it finds a very curvy line, it uses a lot of steps. However, when steps is the chosen method and optimize is turned on, the interpolation engine skips any segments that have a curvature below a certain degree, or where the segment itself is defined as being linear. So if I click on this button, this checkbox, and turn on this option, you can see immediately you lose all of the steps along here. Let's just show that again. And if we go in and edit the spline and go to segments, you'll see that this segment here is a curve and this segment here is a line. If we change it to curve, you can see the optimization doesn't do anything because it's got a certain amount of curvature. But if we go in here and we edit these control points, can't actually see the control handles for some reason. I think it's actually because we've got show end result turned on, so let me just turn that off. There we go. So now, if I change this handle here just by holding shift, so I break the relationship between these two, you can see I can make this more linear. Pull this down to here. You can do the same thing with this line. You can see that when it gets to basically to the point where it is effectively a linear line, you can see that the number of steps is actually dropped to 0. You can see though it actually pops. It's when it reaches a certain threshold. You can see when it gets below this level of curvature here, it's at that point it basically pops down and says that this is a straight line. So you can see those two circumstances control where the optimization takes place. It's either where the curvature is below a certain level or where you've selected that segment and you've told it to be linear. Having this option set gives you some of the advantages of using the adaptive system, but with the explicit control over the number of steps which actually takes place along each segment. Of course, it's not perfect. After all, any segment with any noticeable curvature will have as many steps as you've actually set. It's not adaptive in any way. So in some regards, it's still maybe a little bit brute force. The other issue you have is that when a curve, if you're using some kind of dynamic system animating the spline, as the curve approaches towards being completely linear, the system detects this and chooses to use 0 steps, and that can cause a pop, as you saw, as I just demonstrated just now. Ideally, maybe one day a curvature threshold option will be added to this area of the spline rollout by Autodesk. This would allow us to define just how sensitive the adaptive system is. In this way, if you found the maximum number of steps it used was not enough, you could increase the value and introduce more steps. But for now, we can either choose the steps or the adaptive system. And we can temper the step system by using the optimization checkbox where it's applicable. We now know about interpolation and how important it is in the final definition of the polygonal makeup of our spline-derived models. The vertices and the steps of each segment are used by the spline modeling tools to define our resulting surfaces in 1 or 2 dimensions. So having a firm grasp over how many steps to use and the best system to achieve that count is key to producing models with the correct level of tessellation. Take some time to experiment with the interpolation settings that I've just shown you here, and also, as many of the spline tools are procedural in nature, use that proceduralism to try out different levels of tessellation before settling on a final poly count for your surfaces. So with these concepts under our belt, let's move on and have a look at how we can create and manipulate splines themselves.